Hello, A peers. I'm going to do as many of these review problems I can on the momentum chapter, chapter 9, for the upcoming test. I'll begin with multiple choice question number 1 on page 1. In this question, it says if we know the constant force and time that the force acts, and if we just look at some graph here of force versus time, what do we know if we know force, just force, and time? Well, the quick way to solve this is if you remember that, which you should, force times time, average force times time, is equal to change in momentum. This is one of the principal formulas you should remember. This is the impulse momentum theorem, and what it says is impulse equals change in momentum. So right off the bat, A looks like a winner. Why not change in velocity? Let's see why these are ruled out. Change in velocity requires us, if we know the change in momentum, that means we know the change in mass times velocity of the object. However, in order to know how much of that is due to velocity and how much of that is due to mass, we have to know one or the other. And we don't know mass, it's not given. Just because you apply a force over a time, think about it. You could apply a force for a time on a little brick or a gigantic box. So without knowing the mass, you're not going to know how the object accelerates. Without knowing the velocity change, there's no way to determine the mass of the object. You could be pushing a small object with a larger force or a large object with a smaller force. And also, you don't know the kinetic energy because one of these is squared and one of these is not. Velocity is squared with the kinetic energy, and mass is not squared. And again, you don't know how much of this change in momentum would be mass and how much would be velocity. So A is the answer to number 1. Number 2. An object mass m moving to the right explodes into 2 pieces. Afterwards, we know that 2/5 of the mass is going to go back to the left with half the original speed. So v0 over 2. And that means 3/5 of the mass is left to go at some speed which we want to determine. This is an explosion problem in one dimension. The governing principle is conservation of momentum. The object is not subject to outside forces. These are internal forces. So conservation of momentum, momentum total before the interaction, the explosion, is equal to momentum total afterwards. Before, it's just mv naught, as this is the only object, and then it splits off into 2. The 2/5 m piece ends up going negative v0 over 2. Forgetting that negative, I would imagine, is a common mistake. How do I know that? The word left. And that is equal to, let's see, that's the momentum of that particle plus the momentum of this particle, which has to be 3/5 m. And that's moving times v, which we want to calculate. This ends up being negative 1/5 v0. We can cancel m's right away because it's in every term. So we have v0 equals negative 1/5 v0 plus 3/5 v. Add 1/5 v0, we got 6/5. V sub 0 equals 3/5 v. Multiply by 5/3, you have v equals 2 times v0. E is the answer. Okay, on to question number 3, which asks if we have an object and we have a force on it, and for some of the time we apply a positive 10 Newton force, and some of the time we apply a negative 10 Newton force. What is the total change in the momentum? Now the times are equal, 0 to 2, 2 to 4, and these areas are equal. So what this means is, again, this is knowing this critical relationship, force times time equals change in momentum. So you must know this relationship. This is the cornerstone to this chapter. And really what it boils down to is another way of stating Newton's laws. And it is the force on an object is equal to the change in momentum divided by time. More specifically, it is the net force that equals a change in momentum over time. This is really Newton's second law, because what is momentum? mv. Change in momentum is change in mv when you're talking about one object over time. And if we take change in velocity over change in time, keeping the mass of an object constant means the change in momentum is due to the change in velocity. So change in velocity over change in time is acceleration. So you end up with Newton's second law. Net force equals mass times acceleration. Back to the problem at hand. The change in momentum is equal to force times time, and that is the area under the curve. The area in this part is positive 20 Newton seconds. The area here is negative 20 Newton seconds. Total 0. Newton second is the same as kilogram meters per second squared times second, which is a kilogram meter per second. Again, it has to be that, otherwise this relationship of impulse, force times time equaling change in momentum wouldn't make any sense if the units were different. So the answer to this is 0, as some of the time, if for instance we started object at rest, the positive 10 newtons would accelerate it, and then so if you push it down to the right, and then there's somebody else that's going to also apply 10 Newton force in the opposite direction for 2 seconds, he would be slowing it down to a stop. So if it was, for instance, began with velocity initial, we would have also a final velocity initial, which means the change in momentum would be 0.